discussing about conservation laws. One conservation law that we have already seen is the conservation of charge, which was expressed by the continuity equation, and the new one that we derived last time is the conservation of energy, and the other conservation law is conservation of linear momentum and conservation of angular momentum. So we will do that one today, but before that, we were considering this example, and from previous chapter, finding the ratio of the induction current to the displacement current. And when we calculated the displacement current, so this is how you determine the displacement current. We are interested in the displacement current between current in water that is filled between two parallel plate capacitors that has an area A and separated by a distance N. So if you use the electric field, this electric field has to be the electric field in the absence of water in between the plates. So if you use the electric field this of a parallel plate capacitor, which is sigma over epsilon naught, sigma over epsilon naught, yes, in free space. So if you have two parallel plates, area infinitely large, separated by distance L, the electric field is sigma over epsilon naught, and the surface charge density is going to be whatever charge you have, Q over area over epsilon naught. So if you use this and differentiate the electric field with respect to time, that will give you 1 over A times epsilon naught dQ by dt, and we said this is the free current, right? So this is going to be 1 over A epsilon naught of I free. So if you use that, what we find for JD is going to be what we find is going to be epsilon times by dE by dt equals to epsilon over A epsilon naught times by I free. That's what you get. All right? If you use this relation. On the other hand, if you use the actual voltage, the AC voltage acting on the capacitors, and find the electric field from that voltage, which is going to be the electric field is going to be the potential difference between these two plates, which is V naught cosine of 2 pi nu t over whatever the distance between them, L. If you use that, what you find is JD equals to epsilon times d by dt of this electric field, that's V naught cosine of 2 pi nu t over L. So what you get here is going to be epsilon times V naught times 2 pi nu times by over L times by sine of 2 pi nu t with the minus sign. So you are getting, when you take the ratio of this to the conduction current, to the conduction current, so this, what you get is if you divide IF by A, that's going to be JC, that's the conduction current. So you have epsilon over epsilon naught, that's pi JC. So if you take the ratio of JC to JD according to this result, what do you get? JC over JD, it becomes epsilon naught over epsilon. But for this one, if you just focus on the amplitude, that's the question, what's the ratio of the amplitude of the conduction current to the DC current? So to the displacement current. So JC over JD, what you find is going to be so here from this result, if you use that, what you find is first let's express the conduction current in terms of, okay, so this is what we call the free current, which is the conduction current. So that one, for the displacement current, the amplitude is this. So if I use this amplitude for the displacement current, that's going to be minus let's forget the sign, since we are interested in the amplitude, V naught 2 pi nu over L. So that's the amplitude for the displacement current. And for the conduction current, the amplitude is just V naught over Pn. So V naught over rho L, not there, rho L. And what you find here is a ratio that depends on the frequency. So, so you find L with L, so V naught with V naught. So what you find is going to be rho times epsilon. All right. So this one times 2 pi nu. So this one shows a frequency dependence, but this one doesn't. So the question was which one to use. And if the current is a direct current, if it's frequency dependent, this is fine. We can use this one. This one to find the electric field. The charge, the change in charge is the time dependence of the charge is just only because of the presence of the capacitor. But when you have an AC source that changes the current with respect to time, we cannot use this one because the charge that we would have on the capacitor here, it's gonna be influenced by the time dependence nature of the voltage. So this is fine if it's a direct current. If it's a direct current, that's fine because the charge change here is just due to the presence of the capacitor. But whenever you have an AC source, you must use the voltage to find the electric field in between the plate in the absence of